Today we're going to talk about nonlinear systems. Because we now have a good grasp on linear systems, we want to make sure that we can understand how we can handle it in the event that the system we're trying to analyze is nonlinear. So a linear system, we have some summation of the derivatives of our function is equal to the input of our function or derivatives of the input of our function. And for a nonlinear system, that's not the case. So we could have a turbulent flow, drag, if we have levers where we have sine and cosine. Those are situations in which our system is no longer linear because we're dealing with x squared or different variables such as that. And we've seen lever systems in this class before where we've said that we're going to say that theta is small, and if theta is small, then we can just say that x is equal to our length times theta. Now, if we aren't dealing with theta is equal to 0, or theta being small, how might we be able to handle this? Well, we can think about what we're doing at the start. So we are fitting a line to a curve. So we're saying that the linear version is going to be our nominal value plus the derivative multiplied by how far away we are from our nominal value. And we can also make this completely linear by describing everything in terms of the change. So the change in our linear value of y is equal to the difference between where we want to be and where we linearized around. That's equal to the derivative, so the slope of the line times the change of x. So let's look at an example to kind of clarify what this means. Now, we're going to do y is equal to sine theta because we've done this, but instead of linearizing around theta equals 0, we'll do it around theta equals pi over 3. So the linearized version of this is going to be that we take our nominal value, so sine pi over 3, plus the derivative of sine theta, cosine theta, and evaluate that at our nominal point, pi over 3, and multiply it by the change in theta minus pi over 3. So at cosine pi over 3, that's equal to 0.5. So we can say that the change in our y is going to be equal to 0.5 times the change in theta. So let's look at this with a real example. So if we had turbulent fluid, then we'll have some inlet flow, and this inlet flow is going to be a nominal value plus an oscillating value. And at steady state, we're going to say that our Q in is equal to our Q out, our nominal pressure is 250,000 pascals, and that our resistance is nonlinear. So in this case, we have that it's represented where some of our fluid is going into a tank, and we want to figure out what our relationship between the two is. So we're just going to use a resistor as a R value, knowing that it's nonlinear, but pretending that it has a standard value. If we go through and analyze the system by looking at the change in pressures with relation to our flow rate, we can now find a transfer function just using this electrical model and say that Q out over Q in is equal to 1 over RLCS plus 1. The capacitance of the vat is going to be equal to A over rho G. So this handout is one that's on Canvas. It's linked below this video. And we can also find our capacitance. Oops. I never finished this video. Oh well.